This short recording is going to deal with Ohm's law. Ohm's law was first postulated by George Ohm, a German physicist, around the 1820s or so. He was a mathematician, physicist, and a high school teacher, and he recognized the relationship between voltage and current that today bears his name. This little cartoon gives a nice representation of it. You can see current flowing through. That's a little creature trying to crawl through there, identified by amp, the unit of current, and current relates to the rate of flow of charged particles. The voltage, trying to push them through, voltage or potential difference refers to the push of the current as it flows through the conductor, and the resistance obviously relates to the prevention of current flow, the resistance to current flow, and the little creature there with ohm, the unit for resistance, indicates that. You'll probably remember Ohm's law from earlier years of study. The formula R is equal to V over I has become synonymous with that law. The R stands for resistance, the V for potential difference or voltage, and the I for current. You may also remember that triangle to help you rearrange the formula. R is V over I, V equals R times I, and I is equal to V divided by R. If we now look at the difference between what we call ohmic conductors and non-ohmic conductors. Let's start with ohmic conductors. They are conductors that obey Ohm's law perfectly, so they obey R is equal to V over I perfectly, and that means that the V divided by I, that ratio remains constant. As V increases, so does I, and that means that because the ratio remains constant, the resistance of that particular conductor remains constant. Nichrome wire is a good example of an ohmic conductor that obeys Ohm's law perfectly. So, from a graphical perspective, if we took readings of voltage against current and plotted them on a graph, then as the current increased, the voltage increases. That might be our data set, and that would give us a straight line through the origin. And that shows a direct proportion, voltage directly proportional to current. And if we determine the gradient of that graph, gradient is change in y over change in x. In this particular graph, our y-axis is voltage, our x-axis is current, so the gradient would be V over I. And Ohm's law tells us that that obviously is R. So an ohmic conductor is a conductor that has a constant resistance and gives us a straight line VI graph with a constant gradient, and obviously that gradient is the resistance. If we now look at non-ohmic conductors, those are ones that show no linear relationship between V and I. If you plot a VI graph for a non-ohmic conductor, you won't get a straight line, you'll get some kind of curved relationship. And this, of course, means that the resistance of these non-ohmic conductors changes as the voltage and current change. A light bulb is a really good example of a non-ohmic conductor, and I'll explain now why the resistance of a light bulb changes with time. Once again, if we have a VI graph, if we take some data points for different voltage and current readings, we might end up with a graph that looks something like that. So we have a curved relationship. You can see clearly that the gradient changes, and obviously the gradient of this graph is the resistance, so our resistance is changing. If you consider low voltages and low currents, at that point the light bulb would remain cold, and cold conductors tend to have a low resistance, whereas as the current and voltage increase, the filament gets hotter, and therefore the resistance increases. So you can see clearly here that there's a nonlinear relationship, and the light bulb is thus a non-ohmic conductor. Finally, just want to touch briefly on LEDs, light-emitting diodes. You, I'm sure, see these all over the place. Almost all electronic gadgets that have an on-off switch have an associated, normally red LED that indicates that it's on. and they're starting to be used all over the place now. They're semiconductor materials, and LEDs are becoming a more and more common source of low power lighting. It's a very good low power lighting option, but they're a very good example of non-ohmic conductor. If we plot a graph of current against voltage, notice that the axes are swapped around here. I've got current on the y-axis and voltage on the x-axis. And if we now take different data points, they start to look like this, which is a very interesting pattern. At low voltage, we get no current flowing at all, and then all of a sudden, at a particular voltage, current then starts to flow. And that's a classic profile of a diode, and an LED is no different. But you can clearly see that that's a non-linear relationship. The resistance obviously changes, and so that's a good example of a non-ohmic conductor.